So this is the latest energy scenario in India. As you can see, as on 31st December 2024, we have a 462 gigawatt of installed capacity. So this is the installed capacity, not a generation capacity. In this 462 gigawatt consists of different sectors. Thermal sector, it consists of about 52.9%. Then there is a nuclear power, 1.8%. Hydro power station, 10.2%. Then renewable energy sources, 35%. So we can see that still thermal power sources are dominating. So generate steam, then there will be a steam power plant which produces electricity. And we also have some inputs from lignite, then gas power stations, diesel power stations. So this is a thermal aspect. And another important thing that you look here, here we can see that the share of thermal power plants is coming down. Renewables sources are picking up. This was not the case a few years ago. If you look at some 10 years back, thermal was around 80%, 79, 80%. So now the importance of renewable sources are increasing. So with the issue with thermal, you might be aware of that. It will produce a lot of greenhouse gases. It will lead to pollution and global warming. And if we look at the renewable scenario, almost 35.2% of the installed capacity is from renewable sources. And our national target is to achieve 50% by 2030. So by looking at the progress of these developments, we can ensure that by 2030 this target will be achieved. 50% of our installed capacity, power generation capacity, will be from renewable sources. And we are one of the leading nation as far as the global scenario is concerned. Then our solar capacity itself. Solar is the dominating sector. Solar capacity increased from about 2.6 gigawatt to 97 gigawatt in 10 years. And we have another goal, that is to achieve net zero carbon emission by 2070. This by 2070, all the power generation will be from sources which will not produce any carbon emissions. And this was started with the 2023 Union Budget. In that budget, there was a significant amount of outlay towards transition to clean energy sources, and another significant amount for something called green hydrogen. So we'll be talking about that. So the target for green hydrogen production is 5 million tons by 2030. If you look at the sector-wise breakup in renewable energy, solar is dominating with 60.2%. Small hydro power stations are there. Wind power is another major sector, 29%. Waste to energy is there. Biomass and cogeneration systems also there. So here dominating things are solar and wind. So issue with the solar as well as wind is that these are not continuous source of supply. So these are transient. Day-wise variation will be there. Morning to evening variation will be there. As well as yearly variation will be there. At night it will not be available. In the case of wind, we cannot predict when we will get higher power. All those things we cannot predict. So if we plan to shift to renewable sources by 2070, we have to find a mechanism to store energy. So that is where this green hydrogen, the concept of green hydrogen, has the importance. So green hydrogen or hydrogen in general, we can see that it is the most abundant element in the universe. And on Earth we can find it in several forms, and the total availability of hydrogen in water itself is 10⁻⁴ tons. And in this particular energy transition scenario, we are looking at hydrogen as an energy carrier or energy storage medium. So there is a renewable, there is a transition happening to renewable sources, which is very intermittent and non-continuous generation. So we want to store that. So it is not possible to or it may be very difficult to make batteries of gigawatts capacity. We are talking about gigawatts here. So there are other alternatives like gravitational energy storage systems, all those things. So another feasible approach is produce hydrogen using the excess electricity. Whenever there is excess production of electricity, store that hydrogen, and whenever there is a shortage of power generation, use the hydrogen to produce power. So that is the method in which we will be using hydrogen as a storage medium. Another one is energy carrier. So we can store hydrogen, transport it to, we can generate it at one location and transport it to another location. If you look at solar power plants, these needs a lot of land. So acres of land is required. So in towns and it is not possible to install a solar power station. So what we'll do, we'll generate the power somewhere else, generate hydrogen and bring it to the location where we want to use it. So as a energy carrier medium we can use. So green hydrogen, it is of electrolysis as well as production of green hydrogen. So hydrogen, it can be produced using a equipment called electrolyzer. This is just opposite of fuel cells. In a fuel cell we will use hydrogen to produce electricity. In an electrolyzer we will use electricity and produce hydrogen. So if you want to convert a lot of energy, gigawatts of energy to hydrogen and store it, we need that much big electrolyzers. So there is a lot of research happening on how to develop big electrolyzers. Then also how to produce green hydrogen. So in these two areas, a lot of researchers are going to happen. Then pilot projects are on mobility sector. It is there. Then low carbon steel production. So steel production is another area where a lot of carbon emissions are happening. So in that they want to reduce the or transition to renewable energies required. Shipping projects. Then another things are decentralized energy applications, hydrogen production from biomass, not only renewables also, but from biomass also. Then hydrogen storage technologies. We are developing, generating hydrogen. How to store that hydrogen? That is another big challenge. And we are planning something like 5 million metric tons of green hydrogen by 2030. 60 to 100 gigawatt electrolyzer installations by 2030. Then a lot of new jobs opportunities are coming up. So it is like a new market it is coming up. Then 125 gigawatts of renewable energy for green hydrogen production. We'll be using that much capacity of transferring that much electricity to green hydrogen. Then a lot of investments also expected. And recent developments, we have, so in this mission mode, this first point, transport sector. So whatever they planned in the transport sector, that has materialized. And in November 2024, first hydrogen fuel cell vehicle was commissioned. This was done by NTPC, National Thermal Power Corporation in Leh, Ladakh. So they also plan to operate some 5 hydrogen fuel cell buses. And there is also a hydrogen fueling facility. Just like our petrol pump or diesel pump, there is another hydrogen fueling station also installed there. So that is another important thing. Along with the transition to hydrogen economy, we need hydrogen fueling stations also. So the project has a dedicated solar plant of 1.7 megawatt for providing renewable power for producing hydrogen. So there is a solar plant. From that solar plant, we will first generate electricity. Using that electricity, we will produce hydrogen, store that hydrogen, and use it for running the buses. That is the plan. So this was already commissioned in November 24. And another major step is 8th January 2025. In Andhra Pradesh, there is a 20 gigawatt of renewable energy and first green hydrogen hub with 20 gigawatt of renewable energy capacity. And they are planning to produce 1,500 ton per day of green hydrogen and other derivatives as well. Then 20th January 2025, the Semco Industries, they have signed an MOU with Government of Odisha to explore the development of a green hydrogen physical production facility with a proposed capacity of 7,20,000 metric tons annual capacity. So these are a lot of developments are happening in the national level also. So with that brief introduction, we'll come to the fuel cells. What is actually a fuel cell? So this is, if you look at the figure, it is nothing but it looks like an engine itself, internal combustion engine itself. So it's a electrochemical device. There is electron transfer as well as chemical reactions taking place. It's an electrochemical device which converts the chemical energy of a fuel. So in our particular case, the fuel is hydrogen. So in hydrogen we have the chemical energy, and this chemical energy will be directly converted into electricity. There is no intermediate steps. There is a chemical energy of hydrogen, and that is directly converted to electricity. So there is no losses in between, and it will continuously produce electricity as long as we are supplying the reactants. So if a battery, we are using a battery, it may get discharged. But in a fuel cell, as long as you keep on supplying the reactants, that is hydrogen and oxygen, it will keep on producing. Here it is directly happening. We are supplying hydrogen fuel, we are supplying oxygen, both are burning at a single space. But in the fuel cell, this is happening over an extended length. So that is the advantage. So basically every fuel cell must possess two electrodes separated by an electrolyte. So this is the fundamental thing, fundamental difference between directly burning hydrogen and using the hydrogen in a fuel cell. Is there any doubt regarding any of these aspects? So this is the basic working. Then we'll just compare battery electric vehicles and fuel cell electric vehicles. So fuel cells still, it is not developed that we can directly connect a fuel cell to a motor. Because when we are driving a vehicle, there will be acceleration as well as deceleration. So fuel cell is not evolved to take that load change. Still we'll be using some battery. But currently in the market we have battery electric vehicles. Fuel cell vehicles also there, but they are in the testing stage. So battery vehicle, it contains a large battery to store the electricity. Usually there will be onboard charger, so to convert AC electricity to DC power. There will be an electric motor to propel the car using that energy from the battery. Mostly we will be using lithium ion batteries. That is the industry standard nowadays. And the longest range battery vehicle is Lucid Air Dream Edition, 505 miles we are getting. And fuel cell vehicles, if you see, instead of battery, we will be having a hydrogen fuel tank. Just like our petrol tank or diesel tank, there will be a hydrogen stand for storing hydrogen. And there will be a fuel cell stack to produce electricity. This electric motor in the vehicle will be run using the electricity produced by the fuel cell stack. Then the only exhaust from the fuel cell will be water. And there could be batteries to store energy from the regenerative braking systems. And as far as the experience are concerned, the longest range that we obtained is from Toyota Mirai for 0.2 miles. This is just a comparison of fuel cells and battery vehicles. And if we quickly look into the history of fuel cells, this concept came in 1839. This concept was proposed by Sir William Robert Grove. Then 1937 there was some practical applications of fuel cells. And by 1962, when USA used these fuel cells in Gemini space program, this gained a lot of attention. And maybe by 2000, revived attention on fuel cells as a potential technology for efficient and environment-friendly energy conversion. In 2007, there was commercialization of fuel cells. So in Europe and all, Canada and all, a lot of fuel cell vehicles are there already. And another advantage of fuel cells, it can be used for different applications, from very low power applications like mobile phones to standalone power systems, mobility sector, even one aircraft is there, flying using fuel cells, then trains. So from mobile phones to trains, we can develop these fuel cells as per our requirement. So this first part summary, what is the need for fuel cells? So as I mentioned, we have a transition to renewable energy that is happening, and in this predominant sector is solar sector, solar as well as wind, and both are intermittent. We cannot predict the availability of wind or solar, and at night time solar is not available. So how to store this energy? So excess energy will be produced. How to store that excess energy so that we can use it when power is low, or renewable outputs are low. So that is one of the key aspects. Like we'll be generating hydrogen and storing it, and later we'll be using that hydrogen in a fuel cell to generate electricity. So in this key step, fuel cells are required. And another aspect is efficiency of conversion and environmental considerations. So as I mentioned, the chemical energy of fuel is directly converted into electricity. There is no CO2 generation. Direct only output is water. So water as well as heat. Is the number of electrons per mole of hydrogen reacted. So we have 2 moles of electrons reacting. So H2 gives 2H plus 2 electrons. That means 1 mole of hydrogen will give 2 moles of electrons. So N is 2. Na, that is the number of molecules per mole, or Avogadro number, and Q is the charge of electron. So F equal to Na into Q. So that is 96487, Faraday's constant. So the electrical work will be N into F into V. But once you substitute for Q, we will get N into F into V. As that is electrical work. So the energy useful output obtained from our enthalpy chain, that will be equal to NFV, this expression. So from this we can calculate the basic theoretical voltage of a fuel cell. Voltage equal to changing Gibbs free energy divided by NF value. N is the number of moles of electrons, F is the Faraday's constant. So this is 1.23 volt at 25 degrees Celsius. So you can see this is the theoretical voltage we can get from a single cell. So this is very low value, 1.23 volt. We cannot operate any equipment, anything. So what we do, we will make a fuel cell stack. So we will connect several cells in series. Several cells will be connected in series so that we get a fuel cell stack, and we can, depending upon the voltage that we require, we can keep on adding on cells. So so these are the theoretical value. Actual practical case, we may be getting some 0.6 volt and all from a single cell. So if we want 12 volt, we have to add that many cells, single cells in series. So if we look at a stack, that will have a N plate on the anode side, another N plate on the cathode side, and one current collector plate on the cathode, another on anode. Then all other things will be flow distributor plates in between MEAs, like that. And this is a performance curve of a fuel cell. So this is nothing but voltage versus current density curve. So so theoretically we can get something like 1.23 volt. But if you do experiment, so this red dot shows the experimental values. So if we are testing a fuel cell, we may be getting much lower value. 1.23 will not get. There will be several losses, imperfections in manufacturing. So because of that, there is a drop. So our open circuit voltage will be around 0.99 something. And after that, once you start, so this is at zero current, open circuit voltage. Once you start drawing current, once you start increasing the current output, what will happen? There will be initially activation voltage loss. So this is the reactant, we want to start the reactions. So there is an activation barrier. To overcome this activation barrier, some energy will be lost. So that is taken into account by the activation voltage part. Then, so this is again exponential reduction in voltage. Then we can see almost a linear drop in voltage. This is ohmic voltage because of the resistance of the components, electrical resistance of the components. We have a ohmic voltage loss. So this is in the medium current density region, we can have a ohmic voltage loss. So if you are getting a 0.6 amps per centimeter square current density, you can get that around 0.45 volt. So voltage is keep on decreasing as you increase the current output. Then finally, if we go to the higher current density regions, what will happen? There is another parameter called concentration voltage loss. This is because at higher current densities, the reactions are taking place at very high rate, and we need to supply the reactants also to match that rate. Reactant supply should be at a very high rate, so that only these reactions can sustain. Whatever reactions are happening at that rate, we have to supply reactants also. But not only supplying reactants, we have to remove products also. Product water is there, we have to remove product water from that reaction site also. So because of this mismatch, that is, there is a potential for reaction to take place, but the reactant is not reaching there. Because of that, there will be a sudden voltage drop, which is called concentration loss. So all these three losses, activation voltage loss, ohmic loss, and concentration loss, these three will determine the performance loss in a fuel cell. So generally we will be operating around 0.6 volt. 0.6. Then this is the carbon paper gas diffusion layer. So this is a membrane, and on the anode side we have a so what will happen? Above this we have the flow distributor plates. So flow will be uniformly distributed over this area. So different distributor channel configurations I have shown. Serpentine, parallel, all those things. Each have its own advantages as well as limitations. So when the reactant is passed over this gas diffusion layer, it will diffuse. It will diffuse. This is porous. This is not solid part. It is porous. There is a porosity. Void spaces are there. So it will diffuse to the catalyst layer, and reaction will take place in between this GDL and this membrane at the catalyst layer. There, what will happen? Electrons will be generated as well as ions will be generated. Ions will pass through this membrane to the other side. Electrons will pass through this GDL, come to the flow distributor plate, and from the flow distributor plate it will pass to the copper current collector plate, and from the current collector plate it will go to the, through the external load, it will go to the next side. That is the cathode side. And cathode side will have protons coming from the anode side to cathode side. Oxygen will be there. Electrons will be coming from the external circuit. Everything will react. So this is 25 centimeter square cell. You can just see that, and the current that will be getting is very high in this simple 25 centimeter square. Current may be around 30 amps, 40 amps and all, but voltage will be very low. 30 amps, 40 amp current means the voltage will be 0.2 volt. This is the core component of a fuel cell. Both sides we have gas diffusion layers, and this is a 5-layer MEA I talked about. 5-layer membrane electrode assembly. Two sides, anode gas diffusion layer, cathode diffusion layer. In between, catalyst layers.
What is the capacity output of this particular?
This is 25 centimeter square. So for this only I showed the performance. I did not include the
72 watts, like 0.72 watts.
That range. This particular curve is for this. Power density curve I have not included. This voltage increase 0.6.
Point it is 0.8.
Voltage from 0.6 volt ആണെങ്കിൽ corresponding current density.
അല്ല അങ്ങനെയാകുമ്പോൾ കുഴപ്പമില്ല സാർ 30 ആംപിയർ ഉണ്ടെന്നല്ലോ.
Current divided by 30 amps divided by 25 centimeter. This is current density, not
density.
Current.
Exactly.
So 30 divided by 25 centimeter square. That will be the current density. We may be getting at this value now. 30 divided by 25. Around this.
So what is it?
30 amps of current will be generated. So if it is 25 amps current, then 25 amps of current divided by 25 centimeter square of the area, reaction area. So we will have 1 amps per centimeter square, this value. It will reach up to this. So nowadays fuel cell are going above 1 amps per centimeter square. Above 1 it is going. Better fuel cell. So even some fuel cell will reach 2 amps per centimeter square. That is from 25 centimeter square area will be getting 50 amps of current. So, but that current will be getting at very low voltage. So power density will be very less. Power density curve, that is voltage multiplied by this current density, it will be some graph like this. So we want to operate at this maximum power density point. So that will be something 0.6 amps per centimeter square, all those values. So high current density. This water generation will be also very high. So at the fuel cell outlet we can actually collect water. Current generation will be water generation.
Hydrating this membrane now. That water supply is from that output you are taking.
Two methods are there.
Okay.
That is, there is external humidification as well as internal humidification. So internal humidification is what called dry feed operation. I think I will explain here. So challenge is that we need water to operate a fuel cell, to hydrate the membrane. But simultaneously we don't need excess water. Excess water is there means reactant transport will not take place. That is what my research is. How to use the same generated water to hydrate the membrane. Then thermal management means fuel cell typically operate around 50% efficiency. Theoretically it can have 80% efficiency. So actual practical case it may be operating at 50% efficiency. So the rest of 50% that we lost as heat. So fuel cell will be generating a lot of heat also. So this heat it will increase the temperature of the components. We want the components to operate at a safe temperature limit. So 80 degrees Celsius for this case of particular membrane. If the temperature goes above say 100 degrees Celsius, membrane will get damaged. It will degrade the membrane, catalyst layer, everything will degrade. So we want to keep the temperature of the fuel cell in a safe limit. That is called thermal management. So we want to cool the fuel cell simultaneously. So for cooling what we do, we generally use the reactant itself. We will supply excess reactant. So at a particular reaction rate, we can calculate what is the amount of hydrogen and oxygen required. So we will supply excess hydrogen, excess oxygen, so that excess reactant will cool the fuel cell. So we want to operate the cell with the specified temperature limits by properly choosing the operating, cooling and control strategies. Then if you look at the water transport, so this is the component that I am circulating. This is the membrane electrode assembly. Membrane is the both side we have catalyst layers and gas diffusion layer. This yellow, this is what I have circulated here. So inside there, what are the different mechanisms happening? Different mechanisms are happening. One is convective and diffusive transport of water. So convective, diffusive transport means this flow is taking place, reactant flow. Reactant can carry water. So that is a dominant mode of water transport through the channels. So generally what we do, we will have exclusive humidification systems. We'll humidify the reactant gas before it is supplied to the fuel cell. So the objective is to ensure that fuel cell is properly hydrated. So there is a convective diffusion of convective transport of or forceful transport of water through the fuel cell. Then there is back diffusion. This is due to concentration gradient. So I was said that on the cathode side there will be water generation. Cathode side, hydrogen ions and oxygen electrons, everything will react. Water will be generated on the cathode side. So that part, concentration of water will be higher. So this because of concentration gradient, water will pass from the cathode side to anode side. If on the anode side water concentration is more, means it will diffuse to cathode side. So back diffusion can take place in both directions. Then electroosmotic tract. This is always from the anode side to cathode side. This, as the protons move from
anode to cathode side, they will carry some water molecules with them. That is called electroosmotic tract. Then we have hydraulic permeation. So we are supplying hydrogen and oxygen. So on one side of the fuel cell, suppose pressure is high. Because of this pressure difference, there will be water transport. That is called hydraulic permeation. So we can then because of temperature difference, there could be water transport. So there are different methods of water transport inside the fuel cell. So each we have to consider and optimize. We want our membrane to properly hydrated, but we don't want excess water anywhere here. Excess water will hinder the reactant transport. So other parameters of consideration are relative humidity of the reactant. So as the reactant flow from the
through his publication and leadership roles. Now, let me welcome you, sir. to the session.
Yes, thank you. Thank you for the introduction. And, there is a slight correction in my designation. Okay, facility to be here and be a part of this great program, training program, and giving me the opportunity to share my experience here. Okay. So this is, I think your FDP title is Recent Advances in Electrical and Hydrogen Fuel Cell Mobility. And I think you are emphasizing on the mobility sector, hydrogen mobility sector. Okay. And today I'm willing to share some of my experience on this sector. Okay, and not concentrating on the detailed, not the detailed technical thing. So what I have gathered in my experience in this hydrogen sector, green hydrogen sector, through my very recent opportunity to learn something new in this green hydrogen sector. Okay, and my specialization is purely in electrical engineering, power electronics. And actually, my basic is in instrumentation. I have done my research in power electronics, and I turned over to power electronics, the electrical department, and purely I have been in this electrical department. But naturally, you may think how I'm entered into this green hydrogen sector. So as you all know, this is a very thrust area and a very emerging area and a very fastly growing area. So electrical engineering specialist hydrogen mari enna vishay chindikam, but I will say how I got the opportunity to get into this green hydrogen sector in the final stage of this presentation. But very recently, from 2022 onwards, I have been in this green hydrogen sector in the research. Accidentally, very accidentally. I will share how I came into this hydrogen sector. Okay, so today I will willing to share all my experience. I'm not emphasizing in the purely on this mobility sector. I have included all the things related to this green hydrogen sector, starting from production, some storage, then transportation, and its utilization, like all these things. I will cover all the things in this presentation. Some may be some slides or some areas may be there which you have already been gone through in this training program. If such slides are there, you can say you are all aware of that. Then I will skip that slide. Okay. So I would like to start this presentation, and very first I request you all to not be a patient listener in this training program. Okay, as usually we used to do in this type of faculty development training program. Okay, so this is the time for all of us to think something. So this is the stage where we all need to do togetherly something to this universe, so that we can save this planet. So these all things are towards that. Okay. So we need to remember this quote. Okay. Have you ever heard of this quote? The world has enough for everyone's name, but not for everyone's greed. Have you ever heard this, or the quote is Hume's quote? And this quote is very very relevant in this present scenario. The quote was very old quote, and there is a very big relevance in present situation for this quote. Anyone please? So this quote is from this great man. Okay. Years before he told this. പക്ഷെ നമ്മളെല്ലാവരും ആ ഒരു ഫസ്റ്റ് കാര്യത്തിലാണ് നമ്മുടെ എംഫസിസ് ചെയ്യുന്നത്. വി ആർ യൂസിങ് ദിസ് ഓൾ ദ റിസോഴ്സസ് വാട്ട് ഈസ് അവൈലബിൾ ഇൻ ദ പ്ലാനറ്റ്. വി ആർ യൂട്ടിലൈസിങ് വാട്ട്സ് അവർ നീഡ് ആൻഡ് ഓൾസോ ഫോർ ഗ്രീൻ. We are not bothering about the future generations, and we are not thinking how this planet can be sustained for our own future generations. നമുക്ക് അവർക്ക് എന്ത് കരുതി വയ്ക്കാൻ സാധിക്കും എന്നുള്ളത് നമ്മൾ ആരും ചിന്തിക്കുന്നില്ല. And it is very fastly depleting. All the resources what is available in this universe is very fastly depleting. And as you know, we can't skip the developments in this world. So the development is there. We can't run away from this all developments. Development is there. A big energy is necessary for that. Energy ഇല്ലാതെ നമുക്ക് ഡെവലപ്മെന്റിനെ കുറിച്ച് ചിന്തിക്കാൻ പറ്റില്ല. So energy is needed. But how this energy is, where it is coming from? What are the resources for this energy? And we are using the resources which are depleting. But at one saturated condition, there will not be any resources to create energy in this planet. Okay, so we need to. Please don't see this presentation as a training. Instead, each and every one of you, after this presentation, at least one or two can think what I can contribute towards this. Okay. Yeah. And all this type of things, green energy things, can be started from the SDG. Sustainable. Heavy transportation, and aviation are currently reliant on fossil fuels. Big trucks, aviation, and which are the major consumers of this energy, is purely based on the fossil fuels. They are not at all using the renewable energies. Because of the limited availability of technologies that enable direct use of electricity, until significant improvements are brought into the energy storage density of batteries. Lot of things has to be done. Lot of research has to be done. And here we need a sustainable solution to meet the energy demand for a range of applications across different sectors globally. So here comes the future of energy. ഇപ്പോൾ ഇത്രയും ബുദ്ധിമുട്ടുകൾ നമ്മുടെ മുന്നിലുണ്ട്, ഇത്രയും ടാർഗറ്റ്സ് നമ്മുടെ മുന്നിലുണ്ട്, and the resource, and we are aware about what are the resources what we are using and how we can meet the demand of energy in future. Okay. So here comes the master hydrogen. So with not much of actions were taken already, and we are thinking of different types of renewables, and already the very mature technologies, solar and EVs, that are all there in place. The EVs and solar technology is in place. But even though we will not be able to achieve that target, again emission is there. If we are continuing with the present renewable energy situation, so we will not be, it's 100% sure that we will not be able to achieve that net zero in 2070. So something has to be done differently. So, but it was predicted very before, and it was very beautifully said that in 1874. Okay, just think, very years before, Jules Verne, he predicted that water will one day be employed as fuel, that hydrogen and oxygen which constitute it, used singly or together, will furnish an inexhaustible source of heat and light of an intensity of which coal is not capable. ഇത്ര കൃത്യമായി ഇത്രയും വർഷങ്ങൾക്ക് മുമ്പ് predict ചെയ്തു എന്നുള്ളതാണ്. Okay, so there's a reason why how this hydrogen is going to rule the world. just we can some very basic things regarding this hydrogen. So this is a pressing need. This is a very pressing need to transition towards. We need a very intensive transition, not a simple transition. Very intensive transition is necessary. As we move away from the fossil fuels, renewable energy sources are gaining momentum. Among these, as I said, many renewable things are there, but among these, green hydrogen emerges a promising solution. As we are moving towards the net zero target, so this hydrogen is promising giving a promising solution, offering clean and versatile energy carrier. Okay, I would like to repeat and emphasize on that sentence. Clean and versatile energy carrier. So that sentence is making the hydrogen the different one. It is not simply energy. It is a energy carrier. That is very entirely different. So this gives the versatility of hydrogen. We can see how this is becoming a good carrier. So how, just you think, it is not an energy source. So we can carry this source in different forms. Okay. So with the potential to revolutionize, so that is the reason that somebody is claiming that we can revolutionize these various sectors by using this hydrogen. Okay, and we are all aware of this hydrogen in the school days when we studied the chemistry subjects. ഇതൊക്കെ നമ്മുടെ കടന്നുപോയതാണ്. So do you know where the placement of this hydrogen in the periodic table? First one, periodic table ആദ്യമാണ് hydrogen. Okay, so and some specifications of the lightest element in the periodic table, which has energy per unit mass is 120 mg per kg. The most abundant element, there's another good thing, the most abundant element in the universe. It is abundant, but it's not at all easy to use. Okay.
Safety aspect.
Safety aspect. Any other?
Storage.
Storage means?
Hydrogen storage is very difficult.
How to trade?
No, my question is how to say FCV is better. Even though the efficiency is good for EV, we need to
refueling quick
exactly refueling time.
time.
So for charging it will take hours, so the refueling can be done in minutes.
Yeah, 5 minutes.
Yeah. Yes.
Store it for a long time.
Yeah.
You can store it for a long time compared to batteries.
Battery it will discharge.
Yeah, that's also okay. Any other?
From small input we can produce labs.
Simply we can say what?
Mileage.
Yeah?
Mileage.
Mileage. Mileage means how we can compare this in terms of energy intensive. Which one is energy intensive?
Yes.
Hydrogen or
Hydrogen.
battery? Hydrogen is energy intensive. Okay, so these all consider these all things. Okay, so we can conclude that hydrogen fuel cell EVs are clearly superior to their lithium battery counterpart. There are two major, and that means the first one is weight. Okay, compressed H2 has specific energy of 40,000 watt-hour per kilogram. Specific energy for a compressed hydrogen, the specific energy is 40,000 watt-hour per kilogram. At the same time, for the average value for the lithium battery is 167 watt-hour per kg. Kg per kg le lithium battery hydrogen ആയിട്ട് compare ചെയ്യുകയാണെങ്കിൽ 167 watt-hour per kg, that is almost 236 times. Almost 236 times it is energy intensive. So that is how it is stay differently. Okay, so this is very highly energy intensive, and this is a huge advantage over lithium battery, a technology that drives designers and engineers to difficult trade-offs as the battery weight scales with the energy usage. Why lithium battery cars can take hours to be fully charged, charging time and the fueling time. Okay, so but considering these all things, in present scenario, we can say this H2 CE is maybe better than EV. But some challenges are there. It's okay, it's better. Some challenges are there. We have no efficient method of creating mass amounts of hydrogen. Infrastructure presently three mass hydrogen produce technology. Current methods such as steam SMR, the electrolysis requires huge energy input. Energy input, okay, which has to be generated from somewhere. Renewable solar solar okay, we need to give the renewable input to the electrolyzer. We need that energy source. Solar plant okay, so it requires some space, lot of space is necessary for that. And lack of fueling stations. Fueling stations are so these are all the practical issues. These are the practical challenges now. This is okay, setup by Verino, better. Theoretically, better. These are all the major challenges. And especially challenges in India. Okay, so a lot of I need to skip some slides. Okay, okay. Okay. These are all the challenges. Okay. The main challenges running long distance trucks and buses on electricity or weight of the battery and charging time. Okay. Then. Existing diesel engines can be converted to run on H2 with minimal changes. Hydrogen production plants that is one side, and another one side fuel cell electric vehicle new infrastructure, new technology, already diesel vehicles, trucks already there. Okay. Thousands of crores is already allocated in budget for the green hydrogen policy. Yes. As of March 2024, 6 Indian states, including Maharashtra, Uttar Pradesh, Andhra Pradesh, Rajasthan, Odisha, and West Bengal, have released their green hydrogen policy. They already released their hydrogen policy, and Kerala's policy is in pipeline. Not in pipeline, it has already been completed. In the previous week, the draft of the green hydrogen policy is completed, and most probably by next month, our Kerala's green hydrogen policy will be released. So these are all the milestones, green hydrogen milestones in the government of India. So is about the green hydrogen demand. Okay, the present demand is MTP, million tons per annum. The present demand is 2. It may be in 27 in 2050. 2 million tons per annum, the present demand, and it will be 27 in 2050. In different sectors that are shown. Yes. Another one system is, this is very important because enabling an ecosystem. We discuss the കാര്യങ്ങൾ implement ആയി നമ്മുടെ ഇന്ത്യയിലേക്ക് വരണമെങ്കിൽ we need to create an ecosystem. Each state, ഓരോ സ്റ്റേറ്റിലും അതിൻ്റെതായ ഒരു ecosystem കൊണ്ടുവരേണ്ടതുണ്ട്. So a lot of policies and lot of fundings are there already been initiated by government of India. Okay, and most of the states are very intensive on this creating ecosystem for the green hydrogen. And regarding the creating ecosystem, Kerala is forefront because ഈ കാര്യങ്ങളൊക്കെ ചെയ്തിട്ടുള്ളത്. കമ്പയറിംഗ് ടു അതർ സ്റ്റേറ്റ്സ്, ലോട്ട് ഓഫ് തിങ്സ് ഹാസ് ഓൾറെഡി ബീൻ കംപ്ലീറ്റഡ്. Okay, some challenges, common challenges. Cost reduction is extremely important. ഞാൻ നേരത്തെ പറഞ്ഞില്ല, ഇപ്പോൾ വയബിളേ അല്ല. ഓക്കെ, ഒരു ഗെയിൻ ഹൈഡ്രജൻ പെർ കെ ജി കോസ്റ്റ് $4 വരെ വരുന്നുണ്ട് ഇപ്പോൾ. മറ്റതിൻ്റെ എന്താ കൺവെൻഷണൽ മെത്തേഡിനേക്കാൾ ഇരട്ടി വരും. $4 ഇപ്പോൾ ഉണ്ട് അറ്റ് പ്രസന്റ്. ബട്ട് ഇറ്റ് ഈസ് നോട്ട് ഇപ്പോൾ വയബിൾ. ഇപ്പോൾ നമുക്ക് വയബിൾ അല്ല. ഒരു കോമൺ മാൻ കമേഴ്ഷ്യലി ആക്കാൻ നമുക്കിപ്പോൾ വയബിൾ അല്ല. ബട്ട് അതുകൊണ്ടാണ് ലോട്ട് ഓഫ് ഇൻസെൻറ്റീവ്സ് നെസസറി ഫ്രം ദ ഗവൺമെൻറ് സൈഡ് ആൻഡ് ഇറ്റ് ഈസ് പ്രസന്റ്ലി അവൈലബിൾ. Large scale system studied suitable areas to be identified, large code standards, lot of and this is the reason why a lot of opportunities in front of you peoples there. ഇതൊക്കെ ഇനി ചെയ്യാൻ പോകേണ്ട കാര്യങ്ങളാണ്. Lot of research and lot of support and activities are necessary to build this. Also. Okay, so this is the energy target. 2030. Okay, 500 gigawatt non-fossil capacity. This is what targeting. 2047 energy independence. So that means ഇപ്പോൾ തൽക്കാലം ഗവൺമെൻറ് നോക്കുന്നത് എങ്ങനെ നമ്മുടെ ഇമ്പോർട്ടിങ്, ബിക്കോസ് ലോട്ട് ഓഫ് ദ സോഴ്സ് ഫോർ ദീസ് എനർജീസ് വി ആർ ഇമ്പോർട്ടിങ്. അതാണ് നമ്മുടെ ഒരു ഏറ്റവും വലിയൊരു മേജർ ഷെയർ ഓഫ് ഫണ്ട് ഈസ് ഗോയിങ് ഫോർ ഇമ്പോർട്ടിങ് ദാറ്റ് ടൈപ്പ് ഓഫ് തിങ്സ്. സോ ദ ഗവൺമെൻറ് ഈസ് ലുക്കിംഗ് ടു make the country as energy independence by at least by 2047 and by 2070 net zero. And these are all the national green hydrogen mission. Lot of activities are there. Has ever been discussed in the previous sessions? Yes. I will go through some activities in Kerala. So the net zero vision of Kerala. Okay. So these all visions, these policies are developed under the Ministry of Power and ANAT. എല്ലാ കാര്യങ്ങളും ചെയ്യുന്നത് പവർ ഓഫ് മിനിസ്ട്രിയിൽ കീഴിൽ അനർട്ടാണ്. ഓക്കെ, സോ ദീസ് ആർ ഓൾ ദ നെറ്റ് സീറോ വിഷൻ ഓഫ് കേരള. ദ ഡീറ്റെയിൽഡ് ഓരോ സെക്ടറിൽ നമ്മൾ എന്തൊക്കെ ചെയ്യണമെന്നുള്ള വളരെ ഡീറ്റെയിൽഡ് ആയിട്ടുള്ളൊരു ഡോക്യുമെൻ്റ് ആയിട്ടുണ്ട്. ആൻഡ് ദീസ് ആർ ദ സ്കോപ്പ്. നമ്മുടെ ഒരു കേരളത്തിൻ്റെ ഒരു ജോഗ്രഫിക്കൽ സ്ട്രക്ചറും അവൈലബിലിറ്റിയും റിസോഴ്സും ഒക്കെ വെച്ചിട്ട് നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റും ഇൻ ദിസ് ഗ്രീൻ ഹൈഡ്രജൻ മിഷൻ. സോ ദാറ്റ് ഓൾ തിങ്സ്. ആൻഡ് കൊച്ചി വാട്ടർ മെട്രോ. Have you heard about this? There is a hydrogen boat is there.
Yes.
Okay. So this is already commissioned the hydrogen boat, and another one is under construction. And a lot of initiatives are there in green hydrogen under CL.